Alright, we're back to finish up wave basics by talking about three phenomena that you need to know about as part of this course. And I've got demonstrations for two of them that are on my computer, so I'm going to move this over to the computer in just a second. The first one is beats. So we're going to take a look at a website that I've found, and this is something that you can find as well. Online tone generator, binaural beats. And what this is, when I hit the play button, what's going to happen is you're going to hear a tone. And so you can see that that tone is actually, it's two different tones. If you had headphones plugged in, this would be a little bit different. The left ear frequency is 500 hertz, the right ear frequency is 500 hertz. And just to, again, remind you what that sounds like, it sounds like this. Now, the reason it's called binaural is because I can change the frequency that you will hear out of each ear. Since this is just a speaker, it'll just play both tones at once. I'm going to change the right ear speaker frequency to 501. And I want you to notice how this sounds different. Do you hear how you can almost hear like a pulse, sort of? It kind of fades in and out. Let me raise the right-hand frequency to 502. That sort of pulsing sound is greater. And actually, if you think about the frequency at which it was happening, if you were to put a timer up to that, you would see that there's about 2 pulses per second. If I were to increase this to 503, I bet you can guess how many pulses per second there would be. And if I brought it up to a much higher number, let's say like 510, you would start to hear something where you really can't count the number of pulses per second. And I'll stop that because it sounds pretty annoying. What you're hearing with those pulses, what you're hearing are beat frequencies. So let's go back to 500 and let's go back to just 500. If it's the same exact frequency, you hear an even tone. There's no pulsing to it. If instead you hear two tones, 500 and 501, you hear the sound kind of come in and out with a frequency of about 1 kind of pulse per second. There's a louder point and a quieter point. What's actually happening here is you are hearing a beat frequency that happens because since one of these tones oscillates 500 times per second, the other oscillates 501 times, somewhere in there, the right ear frequency, you have to fit an extra full cycle of the wavelength. Okay, 501 hertz means 501 cycles. The 500 hertz means only 500 cycles. So even though these tones are almost the same, these waves that are being generated are just a little tiny bit off. So that means that at some point there's actually going to be some destructive interference. And at other points there's going to be some constructive interference. The 500 and 500, it was all constructive interference because the waves are exactly synced up. But if we're doing 500 and 501, then that means that there must be one bit of time where there is some destructive interference going on because the waves have to match, the waves can't match perfectly up anymore. And if I increase this number, then the amount of times that they don't match up increases. Now you're going to hear 2 pulses per second, and so on and so forth all the way up. Let's go back to 510 for a second. That's 10 pulses per second that you're hearing. And if you are in band or in choir, you might recognize this sound as, this is what it sounds like when instruments are out of tune. Out of tune means you can hear this beat frequency, you can hear this kind of pulsing because you're not exactly in tune. This is really bad out of tune. So we're going to stop that because it's going to drive me crazy. That's what a beat frequency is. The beat frequency actually tells us how far apart in frequency 2 of our tones or 2 waves are. So let's write some stuff down about that. Okay, the beat frequency. Oh, crossed over my lines. if waves have similar but not equal frequencies, the so-called beat frequency is the difference in F between these waves. And the place you normally hear it is you can hear it in musical instruments as being out of tune. Okay. So let me give you an example of a problem you might see that has to do with beat frequency. If you have, let's say, instrument number 1, plays a note at 520 hertz, and instrument 2 plays at 516 hertz, what is the beat frequency? Well, the beat frequency is simply the gap or the difference between the two frequencies that you're hearing. When there is a gap of 1 hertz, you heard 1 pulse or 1 beat per second. When it was 500 and 503, you heard 3 beats per second. In this case, the difference is 4 beat frequency equals 4 hertz. So we hear 4 what I call pulses. And these pulses, where the sound kind of comes in and goes back out, what you're really hearing is destructive interference. Okay? What you're really hearing is periods of constructive and destructive interference. When the sound goes out, that's when the waves are just lined up, because they're not quite the same frequency. They're just perfectly lined up to cancel each other out momentarily. So those 4 pulses of destructive interference per second. Okay? Beats are pretty simple. Now, let's move on to the Doppler effect. Everyone has heard of the Doppler effect, but a lot of times people can't really explain what it is. And the way I like to put it to help you understand is think about an ambulance that's speeding towards you. Well, at first it's speeding towards you. So this speeding ambulance, when it's coming towards you, you hear a high pitch, and when it's going away, you hear a low pitch. And you can look up videos of ambulances on YouTube, or race cars or police cars going towards and then receding from someone. You'll hear the exact same thing. It's a high pitch at first, or a high-pitched sound, and then as soon as it's moving away from you, it's a lower pitched sound. We're going to talk about why that is. So I'm going to show you another little animation here. So this Doppler effect simulation has to do with this little, this is the object that's going to be emitting sound, and this microphone is the object that is recording the sound. So I'm going to start this with the microphone, or the object emitting sound just in place. So it's going to start emitting sound, and when those waves hit the microphone, you hear like that kind of beat, that clap. Okay, that's just it recording certain points, or recording certain parts, recording wavefronts essentially. And this is just a trick to help us hear, or to notice when these wavefronts are getting to the microphone. Okay, so right now it says the detected frequency is 2 per second. 1, 2, 1, 2, and then the source frequency is also 2. And that's because the source and the microphone are not moving. I'm going to pause this and we're going to restart it. But this time, we're going to have the source move a little bit. Okay, we're going to have it move at maybe half the speed of sound. Come on. Oh my god. There we go. Okay. So now we're going to have the source move, and watch what happens to the detected frequency. It's very high right here as it's moving towards it, but as soon as the source moves past it, now the detected frequency is less than it was. So it was higher, now it's lower. That's interesting. Let's see that happen again one more time. So nothing yet. A lot of waves per second as it's moving towards. Fewer waves per second as it's moving away. And I want you, we're going to look at it again, I want you to look at the spacing on those wavefronts. As the source moves towards it, those wavefronts are not very far spaced apart because the source is moving with the wavefronts. On the other hand, on the other side, the wavefronts are much more spaced apart, especially compared to initially. Here, the wavefronts are evenly distributed everywhere. Okay? And as we increase the speed, oh, I did that wrong. As we increase the speed, what you'll see is those wavefronts push together even more on the front edge and are even lower, or more spread apart, on the back side. So that's a neat little simulation. Okay. Now, to talk about the Doppler effect. That's good. All right, so what it is let's say that I'm going to draw a very crude picture of this. Here's our source. Okay, those are supposed to be concentric circles. Here's our observer. What is happening here is that as the source moves towards the observer, is that the wavefronts in front of the source get squished because those wavefronts are moving at the speed of sound. As the source moves, if the source is moving, then that means that the wavefronts can't get as far apart from each other as they would otherwise. Wavefronts in front of source get, I like to say, squished. As the source moves with them. And again, this happens as the source is not moving as fast as the waves, but it's moving almost, or it's not moving as fast as the waves, but it is moving in the same direction as these wavefronts are traveling. But I do want to point out that it is more slowly. So what that does is it reduces the effective distance between the wavefronts. The distance between the wavefronts is the wavelength. Okay? Imagine this is the crest, this is another crest, this is another crest. It's reducing the distance between crests. That means it's reducing the wavelength. So if we have a smaller wavelength, we're not changing the speed of the waves themselves. That has to stay constant due to v equals f lambda. If v stays the same and the wavelength goes down, then the frequency must go up. That's why there was a higher frequency detected when we did the simulation. There was a higher number of clicks per second as the source was moving towards the microphone. Higher frequency. What happens when the source moves past the observer? Behind the source, it works the exact opposite way. The wavefronts are more spread out. There's a greater wavelength. That means there's going to be a lower frequency. Works opposite. And I should also note that this also works if observer moves instead of source. And it even works if they're both moving. Okay? Now, there is an equation for this, and I'm going to write down the equation. It's going to be useful to you on maybe one or two of these problems, but I think it's a good thing to see, and you might see it if you take more college physics courses. And the equation is it's a little weird. It's a little funky. The equation is f prime equals f times, and a fraction, v sound plus or minus v observer, OBS, and then V sound plus or minus V source. Okay, so this will work for a couple of homework questions that you're going to see. F prime is the observed frequency, the frequency that the observer sees. Observed frequency. Regular old F is the actual frequency, because notice the frequency isn't changing. The source isn't emitting different frequencies. What's happening is you're just hearing the frequency shift due to the motion of the source, either in the direction of the observer or in either towards or away from the observer. Now, V sound is obviously the speed of sound in air in this case, could be in water depending on the media. V obs is the speed of the observer. If the observer is stationary, this is 0. V source is the speed of the source. If the source is stationary, that's 0. The plus or minus has to do with the direction. Okay? So, speed of the observer is plus, you use the plus sign if toward source, and you use the minus sign if away. And that makes sense because if you're using this plus sign right here, then what that means is that the observer is moving towards the source. That would cause a higher frequency, so we want to add these two together. If you're moving away from the source, we use this minus sign. That would be a lower frequency. On the bottom, it's reversed. On the bottom, this is the speed of the source, and it's minus if it's toward the observer, and it's plus if away. Because if the source is moving away, then that should make a lower pitch, so we would want this number on the denominator to be bigger. If it's moving towards, we want this to be minus. And there is some interesting behavior with this part of it, because think about what happens if the speed of the source gets close to the speed of sound. I'll let you think about that one on your own. I'm actually going to stop it. No, I think we can get this done. Okay, so that's Doppler effect. That'll come up in a couple of questions. Let's talk, I don't have a simulation for this next one, so let's talk very briefly about the principle of superposition or interference. This is the idea that waves will pass directly through each other. And we'll demonstrate this in class, okay? They only affect each other when they are overlapping. Once they're done overlapping, they continue on as if nothing had happened. So I'm going to give us 3 examples of this. So let's say we have our first example here. We have some wave pulses, identical wave pulses. They are moving toward one another. What happens when they overlap? Well, the principle of superposition says that the waves, nothing will happen after they are done overlapping. They will simply have moved on without really ever affecting each other. They only affect each other when they're overlapped. So when they're overlapping, what will happen is these waves will actually combine with each other since they have the same sign of the displacement. They're both, I guess you would call them, the pulses are both in the positive direction. They would overlap and they would combine to be bigger than they normally would be. How much bigger? All you do is you add the displacements. So if we had numbers here, I would take the size of this displacement, the size of this displacement. Looks like they're about the same. The overlapped wave should be about twice the height and the same width as the originals. This is known as constructive interference. Interference. Okay, so waves that have the same orientation will build up on each other. What about waves that have opposite orientations? Maybe something like this. What happens when they meet? Well, we know that after they are done meeting, they will look exactly the same as they did before they met. They're not going to interfere with each other once they're not overlapping. And this is a key because you can see from this, the waves don't bounce off each other. Sometimes people think that waves kind of bounce off each other. That's not true. This negative pulse was moving to the left the entire time. The positive pulse was moving to the right the entire time. They have about the same displacement, just in opposite directions. So if we add those together, let's, for example, what happens when you add 4 and negative 4? You cancel out and get 0, right? These waves completely cancel each other out in the middle. They completely flatten each other out. This is known as destructive interference. Okay, constructive and destructive are very easy terms to get mixed up, so make sure you understand why this is happening. Again, we'll do this a lot more in class. Last example, what if you have shapes that are not quite that easy to analyze? So let's say we have like a little triangle-y pulse here, and then a rectangular pulse here, and they're coming towards each other. What happens with them? Again, after they have finished interfering, they will go back to the way they were. The waves will have passed through each other as if nothing ever happened. We've got this wave going this way, this wave going this way, and just like the constructive and destructive parts, all you have to do is add the displacements together and keep in mind their signs. So what I'm going to do is I'm going to make some dashed and dotted lines for this. So I'm going to make a dotted line for here's the left-hand pulse, here's the right-hand pulse. At the left edge, you can see that they should cancel each other out. But whereas the dashed pulse kind of stays at the same displacement throughout, the dotted pulse goes back towards 0, so that even though that they cancel each other out at the left end, at the right end, the pulse is just as high as the right-hand pulse was. So what you get is you actually, if you had numbers for all these points, you'd go through and add them up, and you would end up with something that looks like this. The solid line is the shape that it actually makes. Okay? So we don't need these dotted lines. You can actually kind of scribble them out here. That's the shape that the pulse actually makes. Okay? So the idea behind principle of superposition is that waves will interfere with each other. To figure out the shape, you add the displacements of the wave at each point that they're overlapping. Once they've passed through each other, they continue on in whatever directions they were moving in like nothing had ever happened. Again, we'll get a lot more practice with that in class. But I just wanted to show you the basic idea behind superposition before you get to some of the homework. Okay? I'll see you again when we talk about standing waves. Bye.